Hello students. So today we will understand the motion of dislocation or dislocation movement. Before we go to understand the typical motion of dislocation, let's first discuss a little about the plastic deformation. Plastic deformation is nothing if you have a metallic rod, metallic specimen, you apply tensile load to it and it will elongate, length will increase and diameter will decrease, and this will be non-recoverable, so we are calling it as a plastic deformation. Now what happens if the interatomic spacing is not changed? What happens with this material that its length is increased? That is because every crystal is made up of atoms and the atoms remain themselves in a certain planes. So those planes, if let us suppose these are the three planes, if I am applying a shear force, this could be a step like this. So this length is increased. It's similar to the deck of cards. You apply shear force, then the cards will slip on each other and length will increase and the thickness will decrease. So what is happening? The planes are slipping within the crystal, that we call it as a slip phenomena. Now when we apply a tensile load, because I told you earlier that every polycrystalline material do have dislocations. So whenever we apply the shear force, before these plane slips, the dislocation starts moving. Like this, if this is a dislocation, here is a lot of distortion energy here, right? Whenever you apply a shear force, because plastic deformation is occurring due to the shear force slipping of planes, this dislocation started moving. So this dislocation movement is very, very important to understand the plastic deformation also. So generally whenever you apply shear force, this dislocation move. Now it is written here, a dislocation line cannot end abruptly inside a crystal, but it ends at grain boundaries or free surface. If it comes to free surface, it is no more a dislocation. On other dislocation at a point called a node, on itself forming a loop. So finally, this all things happening when dislocation moves, and dislocation moves under the action of shear force, and it moves at in the slip plane as we seen before. So this dislocation of motion is classified basically into three kinds. One is glide, second is climb, and third is the cross slip. This glide occurs for pure edge dislocation and mixed dislocation. It's wrong here, not in screw dislocation. Cross slip, it is for screw dislocations only, and climb, it is for edge dislocation only. Now we will take one by one these motions. So glide motion, in this glide motion, this is a dislocation present in a crystal. This we call it a slip plane. You are applying a shear force. So in this shear force, this complete slip plane is not moving. But what happening? This is going one step like this. So once it will go on this side, it will make complete plane with this, and this becomes a dislocation. So here this dislocation is moving step by step and like this, and finally it comes onto the surface. Once it comes to the surface, this becomes a perfect crystal, and this is no more a dislocation, but it's a step on the surface step. So this dislocation, when it comes to surface, as it is written before, it could be restricted at grain boundaries or at the free surfaces. So this motion we call it as a glide motion. In the glide motion, if you see the microstructure of a metallic specimen which has gone through with some kind of plastic deformation, you will see slip lines, steps on the surface, which is a clear indication that this how the dislocation moves. So it is written here glide oblique slip and conservative movement. What does it mean, conservative movement? This is the slip plane. When it moves some step forward, the slip plane is this. When it moves some steps further, the slip plane is moved. So if you see in all these three pictures, the slip plane remains same slip plane. So that dislocation is moving on same slip plane. So that's why it is not changing its slip plane. We also call it this is a conservative movement, or it is the glide motion is conservative in nature. In the second kind of motion, which is the climb motion of edge dislocation, in this the dislocation move perpendicular to the slip plane. In glide, it will move like this. In climb, it will move like this. Initially, slip plane 1. When it moves perpendicular upward or perpendicularly downward, it will definitely change its slip plane, and this is a under slip plane. So here, if I make a dislocation like this is the slip plane. Now it is moving down here. Now dislocation is this is the slip plane 1, slip plane 2. So every step it is changing its slip plane. So this dislocation motion is non-conservative. So this is the climb motion. It is moving perpendicular to the slip plane. Now cross slip. So here the representation of cross slip, which says screw dislocation XY moves on the horizontal plane and shifts its slip plane from horizontal to inclined plane, called as cross slip. Means this dislocation also changes its slip plane. So a kind of this is also non-conservative. Now how they change slip plane? Generally, slip occurs in the most dense packed plane, also in the most dense packed direction. This is a preferably they go in those kind of planes. Now to understand this, let us suppose you are having a FCC unit cell. So for a FCC unit cell, so this is a unit cell of FCC. The most dense packed plane for FCC is generally this 111 plane. This is a 111 plane. Right? This is a 111 plane. Now, if you see, if I make another unit cell here at the bottom here, right? The another 111 plane is this plane. So this is the common line here. So this plane is 1 bar 1. Now these two planes are inclined. This is 111, this is 1 bar 1. And this direction, this is, if it is in this direction, it is 101 bar. If it is in this direction, this is 1 bar 01. Right. So when this plane moves, this plane is moving. When this plane moves, it cross slip over to 1 bar 1. So this is that most dense packed direction. This is the most dense packed plane. This plane is moving horizontally. When it comes here, it cross slip to other one. It can be understood like this. So this plane moves and it cross slip to another plane, which is you can consider 1 1 1 2 1 1 bar 1. This is what we understood the how we understand the cross slip.